All right, thank you all for coming out here. And I hope you're just as excited as I am. I have a consumer launch coming up this year in November. And everyone here is going to get a Gear VR as well. So that should be pretty exciting. So I'm Johannes van Waveren. I'm the engineering manager of the Mobile SDK. And I'm going to talk about the SDK. In particular, I'm going to talk about how we changed the SDK over time since we did the first launch December last year. I'm going to talk about some of the rendering that we do, how we actually render in VR, how we do timing, determine basically when you start rendering where it ends up, what time it actually is going to be displayed. I'm going to talk about compositing. Maybe if you watched John talk about things, he talked about compositing as well, layering things on top of each other. I'm going to talk about that as well. And then after that, I'm going to talk a little bit about what we have coming up, what the new things are in the SDK going forward. And that's probably going to be, a fair bit forward. Don't have a real time frame for that, but it's good to be, or at least have that on the horizon and kind of, know what's coming down the pipe. So the first thing is the new SDK structure. The real thing that we try to achieve here is make it easier for developers. First of all, for developers to only include the pieces or the modules that they actually need, and also to allow us to update certain modules without forcing developers to update to a new SDK. So earlier on in the year, one of the things we did was split out what we call the universal menu, which is the menu when you hit the back button that comes up, has a whole bunch of options here, brightness, has the pass-through camera that you can use. So that's a menu that we may want to add buttons, we want to add additional features, and we want to be able to update that without having the burden of all the developers out there having to go to a new SDK, because that used to be part of the SDK. So that's been moved out, no longer part of the SDK, you don't have to worry about it. And then we looked at the SDK and broke it up into a number of modules. So here you have those modules. First of all, we have the VR API, a libOVR kernel, an app framework, and an app support library. And I'll explain what these different modules, what these different parts of the SDK do. So first of all, we have the VR API. The VR API is the API that's used by all engines. Every application uses that one way or the other. It's a C99 API, and we try to make that API as simple as possible. But it's still VR. It's not, there's things that you need to know about it to make really a good use of it. It's a API that has a dozen or so functions, so it's fairly small, and it will do all the basic stuff for you. For instance, one of the things is tracking. There's a function on there to get the latest head tracking information. Also, it deals with frame timing, so it can calculate for you when you have to submit frames and when those frames will actually show up on the display. So frame submission is done through that API as well, and then also the compositing that I mentioned earlier. That is also done through the VR API. So then we have the libOVR kernel. Really, that's just an alternative to STL. If you use other engines and you don't have to use this, we use it for our framework, and that is used by all the first-party applications. It's really basic. It's almost identical to the PC version of that from the PC SDK, and we're going to try to make that completely identical so there's no confusion there. Then we have also the app framework, and the app framework is used for our first-party applications. So we're talking about cinema, 360 photos, those kind of applications. Really the most important thing that it does is deal with the Android life cycles. Android life cycles are not necessarily intuitive to work with, and there's actually two life cycles. So you have the Android native activity life cycle, and you have a surface life cycle as well, so the surface that you actually render to. And those life cycles are asynchronous, they overlap in arbitrary ways, and you have to find basically the spot where they overlap, and then that's the only part where you can actually run your application and display things. So the application framework deals with all of that. It presents a simplified application lifecycle to the application. So that's kind of what we separated out in this library for our first-party applications to make development easier. We're also working on further simplifying that lifecycle on the application side. Right now, at least, it's very well structured. There is a clear order of things and how things happen on there, but we're trying to make it even simpler to where it's really just a couple of functions that you have to be aware of. Then we also have the app support library, and this is a bunch of different things that just make it easier to do rapid development. Once again, we use this for our first-party applications. There's a GUI system in there. There's not a whole lot of GUI systems out there that are very well suited for VR, so this is one of those systems that is in there that you can use. There's model rendering in there, loads FBX files and can render those. Sound management, but it's really just sound management for a GUI system for little sounds when things pop up or something like that, and also handles with, localization. So we also made some changes to how things are built in the SDK. So there's now a couple of pre-built libraries that make it just easier for you, where you just link it in and that's it. You don't have to be all set up to compile it. So the VR API is dynamically linked, and the app framework, if that's the path you go down, that's what you want to use, is statically linked into your application. We also updated the build scripts and made them cross-platform, so it compiles exactly the same way on Windows and Mac OS. So whatever OS you prefer to use, it will be the same thing. So what are really your options on there? I kind of, a lot of the stuff that I just discussed was for first-party applications, or at least what we use for first-party applications. And that's what you prefer to use, great. I mean, that's what we use as well. But it's not really a full-fledged engine by any means. So the other options are Unity and Unreal as more developed engines with lots of support and lots of things going on that make it easy for you to do development. So those are your options you have on there to implement things. But you may have your own engine or a different engine that you want to use. So what happens in that case? So these are the things that we support. We have first-party integration with Unity and Unreal, and then we have native app framework. So if you have your own engine, then we actually provide a couple of samples that make it easier to, or give you a good sense of how you integrate Gear VR support in your own engine. We have two samples. One sample uses a native activity. That's really the Android way of avoiding all the Java code. That's not your thing you want to deal with. You can avoid all of that using native activity. But it makes everything simple, but it's also somewhat limiting. It doesn't give you access to everything. Native activity, for instance, actually is used by Unity and Unreal. So it's definitely a viable option. I'm not discarding it that way at all. Then we also have an app sample that is based on a surface view. It's a different way that the surface is being handled, the surface that we actually render to. That sample does interact with Java code, and there's Java code included there as well. It does all the lifecycle handling, the Android lifecycle handling as well. So that gives you a good sense of how you integrate things with the VR API in particular. So these samples actually only use the VR API. They don't use the app framework, they don't use the app support library, and they don't use the libOVR kernel, the STL replacement basically. These samples also don't use STL. So it really is meant to be something you can look at and see like, okay, this is how I use the VR API if I want to do integration with my own engine. So this is that great sample. This is a bunch of cubes that are rotating, they're colorful, and they're all around you. Not going to win any awards, but that's what it does. And that's probably a good sample to just compile at some point and run through to kind of get a sense of what's going on. There's two compile options in these samples as well. So if you have a multi-threaded engine that you want to integrate Gear VR into, and multi-threaded, it's great for exploiting parallelism on multi-core CPUs these days, but that also introduces an amount of latency. If you want to know how to integrate things in a multi-threaded engine, because it does have some implications as far as like how you use the VR API, then you can define multi-threaded in these samples, and then it shows you how to actually do that. So I mentioned that having a multi-threaded engine, you typically sample the head tracking at the beginning of your pipeline, and you get an image out on the end of the pipeline. The more steps you have in that pipeline, the more latency you have. So one of the tricks is to reduce that latency and make sure that you resample the head tracking right before you submit the rendering commands, so as late as possible. And that's shown as well in this sample on how to do that. Once again, if you use Unreal, if you use Unity, we have first-party integration, you don't have to deal with any of this, but it gives you a sense of how it even works in those engines, because they're very similar in that sense, how the integration works. So let me talk a little bit about rendering and the timing of how things work. How do we actually render, and how do we calculate the timing of all of that? Very important to get these right in VR in general. So this is an overview of the rendering. So on the left side, you see scene geometry and the textures. That's what your artists create. That's what you put into your engine, and you render textures. You render one texture for each eye. It's stereoscopic that you want to show to the user. So you have two views that you render. That's done by your engine on whatever thread is doing the rendering on your engine. If it's a single-threaded engine, it's just one thread. A renderer running in a separate thread could be a separate thread on there. Then you pass those images through the VR API. You submit those images as a frame, and you pass them to the asynchronous time warp on the other side of the API. And I'm going to talk a little bit about the asynchronous time warp, what that does. I'll mention here that the asynchronous time warp and that part of the API runs in a separate thread, and it allows us to do a bunch of different things. And you see that here in the overview where it runs in a separate thread with a separate OpenGL context and everything. So the asynchronous time warp, what does it fundamentally do? Fundamentally, it does two things. It corrects for optical distortion, and it reduces the motion to photon delay. Correcting for optical distortion, the lenses that are in the headset, they are used to bring the display in focus, but they also introduce a level of distortion. And that distortion needs to be corrected for. So we actually project the images onto, or the texture that you render, project them onto the display with the opposite distortion, which ends up being a barrel distortion, which you typically see when you look at like VR images on a screen. And then that goes to the lenses distort it again, and it comes out straight on the other end to your eyes. And then we have to correct both for just regular spatial distortion, but also chromatic aberration. So the different frequencies of light are distorted differently, and they come out differently on the other end. So we have to distort the different frequencies of light differently. The motion to photon delay, or really the end-to-end latency, that's the latency from the latest headset tracking that is being sampled to the images that actually show up on the display. And that latency needs to be very small. We want that to be super small, but it needs to be at least below 20 milliseconds for a compelling virtual reality experience. So the asynchronous time warp also reduces that latency. The asynchronous time warp always takes the very latest head tracking information, so it resamples the head tracking information, then takes the textures or images that you rendered, and it tries to transform those from representing the view that into the virtual world at the time that you rendered those images to a view that is actually the correct view when they appear onto the display and the photons are coming into your eyes. So those are the two important things that a time warp does. So how does that help you? Well, it helps you to deliver a consistent frame rate. The asynchronous time warp is always synchronized with the display refresh. So even if your application is unable to deliver or create or render new eye images on time to stay synchronized with the display refresh, the asynchronous time warp takes the latest images that you have completed and warps them onto the display. So it is synchronized with the display refresh and makes sure that the images are always updated. And in particular for rotational movement, that's the primary thing that the asynchronous time warp does. Rotational movement, it will warp those images and rotate them for you, so it ends up being a smooth view, even if you miss a frame. The asynchronous time warp can also be used to increase the perceived frame rate. So what you could do in your application is actually render, for instance, at 30 frames per second. And then the asynchronous time warp can upsample that and double the frame rate. So every time it takes the last completed eye images or the eye textures that you have rendered and warps them onto the display, and it does that twice, basically, and updates those images based on your latest head orientation to make a smooth view on there. One other important thing that the asynchronous time warp does, which is not necessarily immediately obvious, is that it improves the graphics hardware utilization. So the way that works is the time warp is always synchronized with the display refresh. Your engine doesn't necessarily have to be synchronized. So normally when a rendering engine operates, it leaves a lot of GPU time not utilized just to make sure that it will hit the next, or basically maintain frame rate, and it will hit or deliver the next frame before the next VSync and stay synchronized with display refresh. But now your engine no longer has to do that because asynchronous time warp does that for you. So your engine can now utilize all the GPU that is available and at least try to use it. And if it, for some reason, doesn't actually complete those images in that time, not the end of the world. We still, want to avoid that, but not the end of the world. So to sum it all up, you have more time to render, better GPU utilization. An occasional frame drop is not catastrophic. Think about things like Unity. It has a garbage collection going on, kicks in. Well, what are you going to do? I mean, you miss a frame. Not catastrophic. The asynchronous time warp takes care of that. But performance at the end of the day is still extremely important. If you create an application, you really have to think about performance all the way from the start and make sure that, or try to make sure that at any time you're actually rendering at the refresh rate. That gives you the best and the most comfortable VR experience. So let's talk about the other part of this. So we're talking about asynchronous time warp and what it does, but let's talk about timing. So when you start rendering, or you start your engine, you start your simulation, what time that you start, what time will that what you actually calculate there end up on the display? And that's what we actually provide through the API as well for you to calculate that. Because there is this whole part on the API, the asynchronous time warp, that is not visible to you, so you can't really see what's going on inside. So you want to know basically when things actually end up on the display. So it's really important to have an accurate predicted display time. It's really important because you want to advance your simulation based on when that simulation will be displayed. If you don't do that, you may get object motion jitter. So objects that are moving in the scene, if they're not actually updated for the time they're displayed, then like a character may walk by and it may actually seem to jitter, or sometimes even is perceived as moving back in time. So it's really important that you update your simulation or your animations, etc., based on the time that they will be displayed. It's also important for this predicted display time to be accurate and be as small as possible. We want to have the least amount of latency there. So better predicted display time results in less latency. It also results in less black being pulled in. And what does that mean? So the asynchronous time warp, when it gets the eye textures that you render and it transforms them based on the latest head orientation and it rotates them, well, it has a limited amount of data that it can work with. It only has the textures, only has the data that you actually rendered for the views. So on the sides where there's no information available and the images rotate away, it will pull in black. So the better that predicted display time and the shorter that time is, the less black will be pulled in. And like I mentioned already, you have less motion jitter. In particular, object motion jitter, but also positional motion jitter, because on the Gear VR right now, we don't have positional time warp. It only does the rotational part. So this predicted display time also actually affects the way that the asynchronous time warp operates. So when you calculate this predicted display time, it translates into what the asynchronous time warp actually ends up doing. The asynchronous time warp will never display an image before the time that it was predicted for. And this is really important because if we calculated some time that this is where you start running your simulation and rendering in your engine, and this is the time that that image is going to show up. And that's basically how you set everything up, how you advance your simulation, how you set up your animations. If we end up showing that image early, you get the same problem where you also get motion jitter or object motion jitter, or positional motion jitter, because you're actually not showing the image for the time that it was supposed to be shown, or really the display period that it was supposed to be shown. We also try to not show an image after that time that it's supposed to be shown. But of course, if you don't actually deliver new eye images on time, then we may have to just take the last ones and reproject them and display them as well. So we will do it if we have to, but we try not to. So really, this constrains the asynchronous time warp to one display period where it's allowed to display the images that you have provided. So there's a couple of controls that you have as a developer to influence how this all works and how the prediction works and how much prediction you actually end up doing. I already mentioned if you have a multi-threaded engine, then your pipeline gets longer, and head tracking is typically done at the beginning of that pipeline, and at the end of it, your images come out. The more latency you have there, the predicted display time will go up. The neat thing is that the API will actually detect automatically what the depth of your pipeline is, based on when you request basically the time that things are going to be displayed. So we'll figure that out automatically, but you as the developer can still improve that by basically just reducing the length of your pipeline. The other thing that we actually provide is an option, an extra latency mode. So in particular on these mobile GPUs that are tiled GPUs, they're not immediate mode GPUs. Immediate mode GPUs, when you submit GPU commands, the GPU can pick those commands up pretty much right away and start executing those. On a tiled GPU, however, it's a little different. When you submit commands, and you submit commands for one frame, the driver has to basically accumulate all those commands until it has a full frame worth of GPU commands. And why does it have to do that? Because it has to subdivide all the geometry over tiles, do a tiling pass first. It needs to have all the geometry for that. And only then, once it's done the tiling pass, it can actually start rendering. So there is automatically more latency from a rendering perspective using these mobile GPUs. So we have an extra latency mode, and what that does is, normally, and first-party apps do this because they're all rendering really fast and they're really tightly constrained as far as the latency is concerned. Normally, we have one frame, so one display refresh period that you have for your engine to both generate GPU commands and for the GPU to execute those commands. Now with the extra latency mode, you can double that time. So that does increase the latency, but it gives your application more time to render and to complete what it needs to be done on there. And that, actually is pretty important. Engines like Unity and Unreal that are pretty heavyweight when it comes to, generating or walking your scene graph, doing the culling on there, and generating GPU commands, they're pretty expensive. So they actually need that additional frame to set up everything and then have the GPU also execute all the commands and generate new eye images. Then we also have the option minimum vsyncs. Maybe we should just rename that to frame rate. But minimum vsyncs, really what that means is when you submit a frame, it's the number of vsyncs that will pass before that function will return or allow your rendering thread to continue. If you set it to 1, then it's 1 vsync and you're supposed to render this locked basically to the display refresh. So on the Gear VR, we're rendering 60 Hertz, so you'll be rendering at 60 Hertz. If you set it to 2, there will be 2 vsyncs that pass from you submitting a frame and the API returning to your application. So that means you're going to be rendering at 30 frames per second. So these are the options you have on there. Let's see how it actually works on the timeline. So this is a single-threaded application, just for simplicity. We have extra latency mode turned off, and we have a minimum vsync set to 1. So this is what happens on there. You see like the red stretched out U shape on there, and that's the time that your application has to render, to generate GPU commands, and for the GPU also to execute those commands. The asterisk you see in little stars on there, that's the actual predicted display time. We always predict for the middle of the display period. And the timeline has vertical lines on there. Those are the actual vsyncs. So the predicted display time is always in the middle of those periods. Your application gets released from submitting the previous frame in the middle of the display refresh period, so at the actual predicted display time. Then you have 1 frame to generate your new eye textures or eye images. And then the time warp takes those images and projects those warps them onto the display and does the distortion and everything. So it does that 1 eye at a time. That's why there's these 2 white U shapes on there. And it does that 1/2 a display refresh ahead of when they're actually going to be displayed. So the way that the Gear VR works is it's an incremental display refresh. So things are being updated left to right. It's like a band of light basically that goes across. And the first half of the display refresh is when the 1 eye will be shown and the bar will roll over that, and then the second part is where the second eye will be shown. So the asynchronous time warp renders those eyes separately and tries to just stay 1/2 a display refresh ahead basically of displaying those. And that's what you see on here. So now let's play with these options. So here we have still a single thread application, but now we turn it extra latency mode on. Well, that's pretty straightforward. Now all of a sudden you have 2 frames. That wide U shape, that red U shape on there just doubled in size. Gives your application more time to complete frames. Well, let's turn that back off and now turn minimum vsyncs on. So interestingly, that U shape is still actually double wide. Basically, it's 2 display refresh periods on there because now you're actually rendering at 30 frames per second. But now also the time warp will project the textures that you provide onto the display twice for each eye. So that's why you have the 4 little U shapes on there, 2 white ones for the first time that the textures are being displayed, and then the 2 red ones when they're being redisplayed basically. Because you're rendering at 30 Hertz and the time warp will upsample that to 60 Hertz. So these are the options that you have. And this is all, if you use Unity and Unreal, you don't see this, but it's good to have an understanding of how it works and what goes on under the hood, because it gives you a better understanding of how everything works and how you can optimize for performance. So really, what you want to look for is, well, how do I optimize for performance and what are the things that can go wrong in this case? I explained kind of how this works, but that still doesn't give you a good sense of what you're actually looking for to see the pitfalls. What we have is the simplest way to actually display this data is just because we, in the VR API, every second we just print a bunch of data to the log, to the Android log. So you can just look at that log, and it's the simplest way of doing things. Doesn't require any external tools or anything. You can do this on all the engines. If you have your own engine or Unity on Unreal, you just do ADB loghead and you filter for VR API, and it will show you this data. You want to filter because the Android log gets kind of flooded with information, so you want to just focus on this stuff. And then there on the bottom, that's a whole bunch of information. Don't try to read it all right now. That is being displayed in the log. So let me kind of go over what it actually displays. It displays the frame rate. That's the frequency at which you provide eye textures to the asynchronous time warp through the API. So that's very basic and simple to understand. Then we have prediction as well. That's the time from when you sample the head tracking to the eye textures actually ending up on the display. So that's the total prediction time from head tracking to ending up on display. Don't be completely deceived by this, because this is the time from your application's point of view. In between, we actually have the asynchronous time warp resampling the head tracking and using that to transform the images for the very latest head tracking. So that actually reduces the latency. But still, to avoid like black being pulled in on the sides by the time warp, you want to make this prediction from your application's perspective as small as possible. For instance, one of the things I mentioned earlier is reducing the length of your pipeline of a heavily multi-threaded rendering engine. We also show a number of screen cares in this data. So really what this means is that for some reason, the asynchronous time warp is supposed to stay fully synchronized with the display refresh, but we are not in complete control of the Android system, and we're also not completely in control of what your application renders. We're still sharing a GPU between your application and the asynchronous time warp. You're using the same hardware on there. Even though the GPU is a highly parallel component, it cannot actually execute multiple rendering tasks at the same time. So we still may have to wait for your application to finish certain rendering tasks. This is in particular on the mobile GPUs that are tile GPUs. It renders one tile at a time, and it can only switch between one rendering task to another rendering task on a tile boundary. So if you actually are rendering very expensive tiles in your engine, so parts of the screen, for instance, where you have super high triangle density or something really expensive, a really expensive fragment program, it can delay the time warp. So you have to be careful with that. But also in general, you just want to make sure that there's nothing else going on in Android that is like super high priority and ends up limiting what the time warp can do, and make sure that the time warp can actually kick in on time to stay synchronized with the display refresh. Then we also have the early frames, and the early frames are frames that when you render your textures and you hand them over to the API, to the VR API, to the asynchronous time warp, you may actually be delivering them early. In particular, if you, for instance, set the extra latency mode, you turn that mode on, and now you have like additional time to render images, but you're actually completing all those images on time for less latency. And then you end up delivering those images early to the asynchronous time warp, and those will show up as early images. Don't get, if you see some early images, not the end of the world, but if all the images come in early, then clearly you don't need the additional latency, and then you can reduce latency and for instance, set the extra latency mode, turn that off, and make sure that the images are actually delivered on a reasonable time for when they need to be displayed. The other side of that is still images. They're really late images. So if you're rendering and you're delivering the images late, then that number will go up. And still really means that we're redisplaying previous images, so they're still. We also show the actual values of the minimum vsyncs and that you set on there, whether you set it to 1 for 60 FPS or 2 for 30 FPS. And we have the extra latency mode that you have set on there. So this gives you a reasonable good overview of what's going on, and you can look at these numbers and get a sense of how your application is performing and what you may have to do to optimize your application. So let's go through a couple of common examples here. At 60 frames per second, so your application runs at the full frame rate, but all your frames are completed late. So you're delivering frames at a high frequency, but you're taking too long to complete those frames. Well, obviously you want to optimize. The typical thing you want to optimize for in this case is the time that it takes to generate the GPU commands on the CPU. Like I said, like Unity and Unreal are heavyweight engines. They have lots of features. They, because they're so generic and they allow you to do so many things and give you so much freedom, they're not necessarily all that fast in doing that. So the more you optimize that, the better, and the better your application will work on making sure that the frames are not actually delivered late. So the other thing is, if that continues to happen, then you can increase that extra latency mode and give your application 2 frames as opposed to 1 frame to or display refresh to complete and render frames. Another example is, well, you're not even rendering at 60 frames per second and you're delivering the frames late. Well, once again, first thing you want to do is optimize. The other option, if optimization is you have optimized everything that you think you can optimize, is considering running at 30 frames per second. And actually, even if you run at 60 frames per second, you can still consider running at 30 frames per second in some cases, because it can significantly reduce the power draw from the device which in return, increases your battery life and reduces the amount of heat that you produce. So there can be a way in general to improve your application from that perspective. Then again, you still get the best VR experience and the most comfortable VR experience if you actually render at the full display refresh rate. So you render at 60 frames per second. I already went into the screen tears a little bit on what you have to do there. Make sure that there's nothing in Android going on. We run with SCED 5.0. We have locked clock frequencies on everything. So we should be in really good shape to make sure that the asynchronous time warp always stays perfectly synchronized with display refresh. That's what we want. Hopefully one day we'll have Android in complete control and we'll actually be able to do that. But as it is right now, there are still ways that your application can cause the asynchronous time warp to not stay fully synchronized. So you want to keep an eye out for that. If that number goes up, then you want to look for that. One thing to mention on here also is that when you first launch your application, things need to stabilize a little bit, and you may see these numbers kind of go up, and then they go down, and a lot of these numbers, for instance, like still frames and the number of screen tears will just all go to 0, and then they will stay at 0 for your application. Now, that's a very primitive way to look at the data and to get a good sense of performance. That's just looking at the Android log and looking at this one line that the VR API actually prints out. Another option that you have is, and that's what I would consider the high frequency option. So the VR API prints data once a second. What you also can do is actually inspect things more like in a nice overview. So we have the VR capture library. It captures a lot of data. It's integrated with the VR API. You can integrate it with your engine as well to capture data there directly. It actually captures the Android log as well, but it also captures OpenGL draw commands and all that. You also have certain variables in your code. You can actually change them on the fly to see how that affects your application. And really the idea here is that this capture library captures enough data and captures it really fast so you can analyze that data offline and get a good sense of what your application is doing. So how do you analyze that data? Because capturing it is one thing that's nice and neat, but how do you visualize it, how do you analyze that? Well, you do that with the OVRMonitor tool. This tool runs on both Windows and Mac OS, and it takes the data that is captured by the VR capture library and displays it in a way that you can actually make sense of it. It automatically finds the capture session that's going on the network, or tries to anyway. You can connect to it, and it visualizes all the data in real time. It's basically one big timeline. You see all kinds of stuff coming by. You can scroll through that, you can go back in time, and you can really get a good sense of what the interactions are and what the dependencies are between GPU and CPU and how things all line up in time. So let me have a look at that, what it actually looks like in the tool. So here's an example of the profiler view. So really it's a whole bunch of timelines that are scrolling from right to left. The capture tool captures screenshots, so you can actually correlate what's going on in your application with this data. So at the top here, you see a whole bunch of screenshots. It's tiny in this view, and also those images are actually compressed down just to save bandwidth. But it gives you a sense of what's going on in your application. And then you can see what's going on the GPU with GPU timer queries. You can see what's going on the CPU, on the different CPUs that are running there. You can also see the actual CPU clock frequencies. That's pretty important because if your clock frequencies are set too low, or if in power save mode they're actually clocked down, that may affect your performance too. And you can also see the temperature of the device. So it gives you a really good overview of what's going on. So if you're trying to optimize your application, I recommend that you load up this tool, and this works in Unity and Unreal as well, and gives you a good sense of what's going on, and allows you to find the hotspots and find the things that you may be able to optimize. So another important part of the SDK is the asynchronous time warp compositor. I talked about the asynchronous time warp and what it does, but it does a bunch more. And John mentioned that in his keynote, how he took advantage of that for displaying a HUD basically, and making sure that the HUD always stays locked to your eyes, while the rest of the world can be updated by the time warp for the latest head position. So let's first, before we go into the details there, look at what the actual details are of the device. We have a 2560 by 1440 display. In the very middle, in the center of your eyes, the pixels cover approximately a 0.06 degrees of visual arc. So you need about 6,000 pixels to cover the whole 360 around you. If you have a 90 degrees FOV, which is about what the Gear VR provides right now, then you need about a quarter of that. So you end up with about 1.5K eye textures. And that gives you a good one-to-one mapping in the center of your eyes. However, it does not give you a good one-to-one mapping closer to the edges, to your peripheral vision. And you will actually need maps on those textures to get a better one-to-one mapping. So what we actually do, and what we recommend that you do, is use 1K eye textures. So these eye textures don't need maps, so you don't spend any time creating maps because that's not for free. Also, you render at a lower resolution, so it's just a lot faster. And these eye textures may not have a perfect one-to-one mapping in the center of your eye, so you get a little bit of stretching on there, but you don't need maps on the edges. We do recommend that you use multi-sample anti-aliasing on there. I recommend 2x or 4x, and it kind of depends on which device you have. The API actually provides a function to get a system property that tells you which mode of multi-sampling, either 2x or 4x, runs at full speed on the device. So in that case, like for instance on the latest S6, 4x multi-sampling is practically for free as far as actual rendering cost on there. So use multi-sampling to make everything smooth. Like John said as well in his keynote, is that any kind of aliasing that you have going on is extremely visible in VR. So it's really good to get rid of that. However, do not turn on multi-sampling on the front buffer because that's completely wasted. The front buffer, the time warp takes the images that you've rendered in your application, warps them onto the display, and actually just puts every pixel directly onto the front buffer. And there's no point in doing multi-sampling anti-aliasing on there. It's completely wasted. So even though multi-sampling may be practically for free, it still takes up bandwidth and all that. So we still want to avoid it there. So let's go back to the rendering overview that I showed earlier and what it actually means in there. What we have going on in there. Same overview. Now you have the numbers that we actually use, the sizes of the textures, and the size of the front buffer, and no multi-sampling on the front buffer as well. So that's kind of the overview of how that works. So, but that's all nice and neat. So, it sounds like we have a good solution, but there is a downside to using lower resolution eye textures. It does mean that we get some level of undersampling in cases. When you render your source geometry with textures, that's where we sample the textures, the source textures, once, and we display those, we project those onto the eye textures that you render. Then when the time warp takes over, it takes those eye textures, samples those again, and projects them onto the display. It samples it again. So you have double sampling going on. If those eye textures are low resolution, you lose some level of quality there. So really, the lower we go on the eye texture resolution, the more you're going to see artifacts because we're doing a double sampling. So what's the solution to that? Well, the solution, or one solution at least, that allows you to get better quality in a variety of cases without increasing the resolution of your eye textures is to allow the time warp to directly sample source textures. So we have two common cases there. That is a 2D texture that is sampled on a head track plane. That's a typical example for like a movie texture that is directly sampled in the time warp. We also have cube maps that can be directly sampled. So if you have like a skybox, for instance, then you can sample that cube map directly. It's projected onto a head-tracked cube, and that gives you much better quality. And a really good example there is a cube map, for instance, with stars. There's tiny little dots. If you double sample that, you get all kinds of artifacts, and you see like blinking stars, basically. If you sample that directly in the time warp, you can get much better quality. So here you see that in the overview, the time warp can actually sample certain textures directly and use those directly and improve the quality without you having to increase the eye texture resolution and lose performance or produce more heat that way or reduce your battery life that way. So how do you submit these additional textures? Well, the time warp, the way it is set up, the way the interface is set up, you submit your eye textures, and you can also submit additional textures that are directly sampled by the asynchronous time warp. The alpha channel of either the eye textures or the additional textures that you submit as additional layers, that alpha channel controls how things are blended together. Also, we allow you to specify a rectangle in texture space. That's the actual texture space that is being sampled. So you can limit the amount of texture data that is being composited and being blended together. That's a pretty important option, actually, that allows us to save quite a bit of performance in some cases. In particular, for instance, for movie screens that usually don't cover the whole screen. So we can limit that texture space on there and only do the compositing in that limited region. So these are the typical examples. A high-quality cube map background. I already mentioned that. And high-quality movie screens, very important there. In particular, if you have subtitles, for instance, you want to have the subtitles very crisp and good looking on there. If you render them first to the eye textures and then you sample them from there, you may get all kinds of artifacts, and it may not be easy to read. So it's important to do it there. Another option is the one that John was talking about, is a heads-up display. You may even be able to save some perform or improve the performance there by only updating a heads-up display whenever it needs to be updated, and then providing those images to the time warp, always providing the last completed images. For instance, you can update the HUD at 10 frames per second or something like that if it's not a big burden for the user experience. So that's another example. So here you have a couple of images that show those examples. 360 photos is a typical case where we use those layers. The background is a cube map. It's directly sampled by the time warp. It gets really high quality on there. That cube map is effectively static, so we use 1536 cube map size, and we actually have mip maps on there as well. So you get super high quality on there. They're only updated when the images are loaded, and otherwise it just displays them. Then you see a menu on top, and that menu actually is rendered to the eye textures as it is. And that menu is then using the alpha channel blended on top of the cube map. So that's a typical example where you have this compositing going on and you have much better quality because the cube map is sampled directly by the time warp. Here's another example, cinema. You have a movie screen in there. That movie screen is directly sampled by the time warp. On this movie screen, you actually see some text as well, and there's a really big difference in quality and reduction of aliasing because that movie texture is sampled directly by the time warp. And it's fully head tracked as well, so it fits in nicely into the scene, and you don't see any, from a user perspective, you don't even know that it's being directly sampled. So what other things do we have going on? So a lot of details about rendering and compositing. We have a bunch of new stuff coming up as well. I mentioned earlier that we don't have a solid timeline for that, but these are things to keep in mind. Some of these are lower level things that you don't have to worry about too much if you use an engine like Unreal and Unity. And hopefully at some point you just magically get these things and they'll improve performance. But they are coming up, and it's good to be aware of that. So one of the things is, Google is deprecating Eclipse and Ant as their optional compile environment. So we'll have to update. We'll have that all set up for you to use Android Studio and to use Gradle. And we'll have a migration guide as well to help you transition from the old way of building things to the new thing, to the new way of doing things. We also have the new graphics API Vulkan coming out. So right now on the Gear VR, we use OpenGL ES. That's the rendering API that we use. All the engines like Unity, Unreal do that as well. The hope, of course, at Vulkan is that it's going to significantly reduce the CPU time that is spent to actually generate GPU commands. So hopefully we'll be able to allow you to run at lower clock frequencies, save power, increase your battery life, all those good things. So hopefully that will come out of that. Here are some other things that are coming up. We have a multi-view extension. What this does is allows you to also reduce the CPU time that is spent to generate your eye textures. Multipass asynchronous time warp compositor. The way that things used to work is it was kind of an Uber shader where you had these fixed combinations of layers and how you can composite things together, a fixed way of doing things. Now it's more generic and it's much simpler. And the multi-pass compositor also actually allows us to significantly improve the performance. This is where that rectangle in texture space that I mentioned earlier comes in, which is one of the things that the multi-pass compositor allows us to actually work or function properly. If you have an Uber shader for every single pixel on the screen, it does the compositing, does the blending. If you have a limited range of texture space that is being composited, you can actually save a lot of rendering time. And that's time that is not necessarily directly visible to you because not time spent in your application, but it's rendering time spent in the asynchronous time warp. Still very important. In cinema, for instance, it saves multiple milliseconds of time. We also want to expose the asynchronous time warp compositing to Unity and Unreal. So right now, those are not exposed. We want to expose that and give everyone the freedom to composite things. For instance, have that heads-up display if they really want to, that is locked to the screen or locked to your head, basically, while the rest of the scene can be updated by the asynchronous time warp. So we're trying to come up with a good way to present the same interface from a Unity and Unreal perspective that you have in the native applications that we have, or first-party applications. We're also further simplifying our application framework, if that's what you prefer to use. Like I said, it's not a full-fledged engine by any means, but we use it for our first-party applications, and it definitely allows you to do some neat things. The legacy Unity integration is going to be phased out. It's going to be the first-party integration only. That's what we're focusing on. Right now, we still support it because we know that there are some engines and some games in development that they have a really hard time to switch over to the new version of Unity. There's differences in like how light maps are generated and all that. So we will support this for a little bit, but it is going to be phased out. We're not going to support that forever. So if you want to do something new, use the latest version of Unity. Use the first-party integration. So let me go into the multi-view a little bit. That's a really important extension or development for us. So really what is the problem? We render stereoscopically, we have to render 2 images, and those images are actually not that different. Yes, okay, they're different, the eyes are slightly offset, but at the end of the day, they're strikingly similar. So if you render those images the normal way, then you're really just spending twice the amount of time. So what we want to do is, we want to avoid that. So that's what the multi-view extension does. We want to basically render both views at once. So really what we want to do initially is just make sure that we only have to submit the CPU commands to render those images once. And then the driver or the hardware or whatever ends up being done behind the scenes for you does or actually renders 2 images at the same time. So this is exactly what the multi-view extension allows you to do. It allows you to submit the CPU commands once, and then it will render 2 images, significantly reducing the cost in your engine to render images. So what does that look like? Because it does require you to make some changes to the Vertex shaders, the way they are rendered. In the Vertex shaders, as opposed to having 1 view matrix, we now specify 2. This is an example where we render with a model view projection matrix that is actually multiplied inside the Vertex shader. That gives you the best precision. And this is a case where we have 2 view matrices, and we have the GL view ID, which is part of the extension that is being updated for each view, and it allows you to index the right view matrix. So this still clearly shows you that from a rendering perspective, behind the API, everything is done twice, but from a submission perspective, submitting CPU or GPU commands from the CPU side, it's only done once. We also in here specify the number of views that are being rendered, because on some of the devices, there is a benefit to knowing beforehand how many views are being rendered, so these shaders can be optimized appropriately. So here's the example. If you actually have a pre-multiplied model view projection matrix, you can still use the extension and apply a slight offset based on the separation between the eyes. So this is the API extensions, so the OpenGL extension, the OPL functions. Really what it does is it creates a frame buffer where an array texture is attached as opposed to a regular texture. So and each eye is then rendered to one of the slices of the array. Slice 0 typically, and slice 1 for stereoscopic view. So you specify the number of views on here as well, and those are all the things that are highlighted on here. That also means that if you submit your CPU commands once, that you actually have to do everything once. You run through your scene graph once, you do all your culling once as well, because you're only submitting the CPU commands once. So normally when you have your stereoscopic view, you do everything per eye, which means you have a separate view matrix for each eye, and you do your culling per eye. So normally you cull based on those view matrices, and you still have to provide those view matrices through the API, but now you want to do culling once that includes both views. So how do you do that? Well, the simplest way to do that is to calculate a new view matrix effectively that is the center eye position in the middle of the 2 eyes, but then pushed or pulled back a little bit so it includes both views. So that's kind of what's shown in here, that you can easily calculate a new view matrix that is pulled back and includes both views on there. So there are a couple of downsides to this extension. The extension is great. I mean, it does wonders as far as reducing the amount of CPU time spent on there. But the first implementation of that extension, you can only modify the geo position in your Vertex shader. And that means that if you have view-dependent lighting effects, you cannot actually change those. You can only change the position of your fragments. The Multi-View 2 extension, and we had a first extension just to make it easy to integrate for all the hardware people. We have a version 2 of that, and that does allow you to modify more parameters. So you can actually do view-dependent lighting effects as well. It does need OpenGL 3.0. There's still some engines out there that are using OpenGL ES 2.0, some engines that are focusing on a wide variety of things, not just 3D rendering, but also 2D rendering, for instance. You also have to modify the Vertex shader, so it's not completely for free. It's not just a little knob you turn on and then you magically get everything for free. It has to do a bunch of stuff has to be done on there. If you use Unreal or you use Unity, then the hope, of course, is once that's fully integrated on there, that you just pretty much get all this for free, which is great. The other thing is, if you're GPU limited, you can optimize the CPU side all you want, but it's not necessarily going to improve your frame rate. Then again, you have to realize as well that typically in VR, you can pretty much optimize forever because you can always reduce the amount of power draw. And that increases your battery life and reduces the amount of heat that is generated. So even if you're GPU limited, it may still be worthwhile to optimize the CPU side because you can run a lower clock frequency and you can improve your battery life, which, if you want to run an application for or your game or your entertainment, whatever it is, for an hour, then battery life is a big thing. All right, I have some time for questions, if people have questions. Yes?
Not replaceable battery, Note 5. How's that going to work out?
So the question is how on the Note 5 not having a replaceable battery. It just means that you have to charge it. On the headset, though, there is a slot as well that you can plug in to.
While you're actually using it?
That's a good question. I don't know the answer to that directly, but I think so, yeah. Yes?
What's the likelihood in the near future of being able to do development for other mobile platforms, iOS or other Android platforms, not in Samsung Gear? I'm thinking there of various holders that you could put, say, a Project Tango device
right.
up in front of you.
So, you have to realize, first of all, that if you want to have a really good VR experience, then you're going to have a headset that is, made for the device. So if you have different sizes of devices, you can't just make one universal headset that has like the right lenses for all of that. Right now, we have a really good relationship with Samsung, so we don't have any near future plans to support other devices or other headsets.
Thank you.
Hey, how's it going? I'm Greg from AltSpace VR. We actually recently got our stuff running on the Gear, and one thing that has come up is no matter what we do, it seems like this fixed CPU throttling is not actually working. It seems that the clock rate is in dynamic mode the whole time, and we've seen under low load, we actually get tearing from the time warp,
Okay.
and actually when we add load.
Are you running in developer mode?
No. So we actually verified with a fresh reboot without developer mode on that
Okay.
it's still in dynamic.
Yeah, because there is a known issue where if you run in developer mode, then at some point the clock frequencies are released. And
Right,
it actually
so-
becomes dynamic.
So is there any other things that you guys might know about? I know we are doing one.
There's one other thing on the I'm not sure if it's an S6 that you're using on there, but on the S6,
It's only on the S6 we see that.
yeah, so there is a little bit of leeway on there. So I believe that is set up for particular Unity, where you have effectively a fixed clock frequency, but can still scale up a little bit.
Okay.
But
Would
I'm
that
not sure
affect
that's
time
what it is.
warp when it's on the low side? Because we've been noticing tearing is kind of like inversely correlated to how high the CPU goes.
Okay.
Could that be part of that?
The tearing, you mean?
Yeah, we.
Yeah, so if you overall have not enough CPU to make sure the time warp actually stays synchronized display refresh, and yeah, you will get tearing.
Okay. Okay. I don't know if that. Yeah. Can help.
Right. Yeah, otherwise you have to just come after the talk and
Okay.
check up with me, and we can actually have a look at that.
Cool. I have one quick follow-up question. When you guys are looking at integrating the compositor into the game engines, are there any plans to introduce like depth buffer so that there'll be some type of occlusion? Or right now it looks like there's not a clear way to do occlusion.
Yeah, that's a big problem on the mobile devices because that means we have to resolve the depth buffer.
Right.
That's a lot of bandwidth.
Okay.
So right now we don't have anything that we are thinking of. So not occlusion, but also if you have the depth buffer, you could in theory do positional time warp, for instance.
Mm-hmm.
And we don't have that planned as it is right now,
Cool.
just from a bandwidth perspective.
Great. All right. Thank you.
All right.
Hi, great presentation. My name is Mark Cafano. I was wondering, can you talk at all about the different chunks of technology that that are Oculus, Gear VR, and sort of where, from this processing conversation you talked about, where they are on the device?
And so what are the different processing? It's
what lives in hardware, what lives in software?
Okay, it's one integrated piece. It's one SoC that we actually deal with. So a GPU, a CPU, it's all on one piece of silicon. On the software side, so the VR API, obviously we implement that in software as it is right now. Compositing is done in software. We use a GPU for compositing to actually blend the different layers together, but we submit all of that from the CPU side. Normally, if you have Android and you do compositing on there, you have 2D compositing going on, then there's actually a compositor in the hardware as well. But it's set up for 2D rendering, not for stereoscopic VR rendering. So we're not really able to use that in an effective way. Is that going to change in the future? Maybe, I don't know. But so that's kind of where the engine mostly runs. All the GPU commands are generated on the CPU. It's still the same SoC that is executing all of that. It's really just one chip. We're not using any DSPs or any other components of the device. And the headset has its own sensors for getting the latest head tracking and all that is sent back into the phone as well. Does that kind of answer your question?
Yes, it did, thank you.
Okay.
Hi, I'm Chris. I was interested in the multi-view GL extension you were talking about.
Okay.
I think that's kind of interesting. I was wondering if you could maybe talk about some of the advantages, like why push another extension over maybe a geometry shader and an instancing type of approach, like what the advantages there are.
Yeah, sure. So the geometry shaders are generally expensive, so they really slow things down on some hardware. So we try to avoid that, and also we don't want to exclude the geometry shaders being used for other things. So we don't want to be in the way there. Adding this extension was really the simplest way and the easiest way for all the hardware people to extend their drivers and make this all work, as opposed to using the existing geometry shader on there.
All right. And then one more quick thing.
And the extension, you can look it up online. It's on the registry
Cool.
for OpenGL.
And then I was curious, this compositor you're talking about, sampling textures during time warp, all that, is that in VRLib?
That used to be VRLib, but it's now inside the VR API.
All right. Thank you.
So whenever you submit a frame, you actually submit a frame as a set of layers, and those layers get composited together, so it's all done in there. So it's done in asynchronous time warp inside the VR API.
Thank you very much.
Yeah, welcome. Anyone else? Any other questions?
Yeah,
Go ahead.
I have one more question. So the asynchronous time wrap that you talk about, that you can sample inside the time warp, can you change the GL texture ID at each frame, or you have to use a static texture?
So we changed the API a little bit, and that was to get parity with, or better parity with the PC API. We're trying to make those APIs very similar to make it easy for people to look at both APIs on the PC side, on the mobile side, and there may not be exactly the same the way we release it, but at least if you look at them, you'll know, okay, this is very similar, and this is how it works on one side, and it works very similar on the other side. So one change we made is that if you have the eye textures that are rendered to be updated, that typically are used to render the 3D world, that are updated every frame, those are allocated through the API now. And that's a thing that it has to be done on the PC side, because they have a system service level compositor, similar to our compositor, but our compositor is not system level. But yeah, you can actually, every frame, provide different textures. You just have to allocate them, obviously, and provide different texture IDs through the API and composite those together. There's no need for those to be the same. So every time you submit a frame, it's a whole bunch of data that you provide, and that's data really that you provide with texture IDs, different layers, everything you want to blend together, how you want to blend it together, and then the time warp just goes off and does it for you.
Okay, thank you.
So this might be a yes or no question,
right.
but if I wanted to be able to pull a monoscopic monitor off of the Gear VR SDK, I mean, is it possible to get it out of the eye buffer or before the eye buffer? Is that exposed in any way?
So, I mean, on the application side, you can take one eye, basically, and use that. Before you actually pass things down to the VR API to submit a frame. The capture library, however, also captures one of the frames, but it's low resolution, so it's probably not of a whole lot of help for you. You probably just want to have like a high quality monoscopic view of that game.
Just pretty much so that we could see like what the person in VR is seeing, but maybe on a laptop.
Yeah, so you can actually use the VR capture library and the OVRMonitor tool for that if that's what you want.
Oh, perfect. Thank you.
Yeah, and then those frames, and you can kind of zoom in on there. But like I said, they're somewhat low resolution, which is unfortunate, but we have to do that to save bandwidth, because it takes up a lot of bandwidth otherwise.
All right, thank you.
All right. Anyone else? Any questions? Right.
or Unity or Unreal, if there's any, you know, 'cause it's
We'll continue to work on that. Like I said, we want to kind of clean up the application lifecycle on there as well. You can do some very minimal level of like animation and moving objects through FBX files, but we don't have a full-fledged animation system in there. Do I see that happening anytime soon? No, not really, because those kind of things, that would be more on the app support library side of things. Those kind of things are really driven by our own needs for the first-party applications. So unless maybe we come up with an application where we're like, okay, we really want to do this, then yeah, sure, we'll spend the time and do that. But as it is right now, like Cinema and 360 Photos, for instance, they don't have, animations going on. I mean, actually in the box office scene of Cinema, you have like the lights and whatnot that are moving. You have a couple of things that are moving around, but that's not really a full-fledged animation system. That's just a couple of components that are moving. So no direct plans as it is right now. But yeah, I mean, at the same time, that code is all available for the app support library. So if anyone wants to go crazy on there and add something, that you totally, you can do whatever you want.
Thank you.
All right. Anyone else? Okay, go ahead.
My name is Casper, and I just wanted to ask you about heat generation and management. I know that from the Note 4 there was no fan integrated with the unit on the Gear VR. Then
Right.
You guys on the S6 finally put a fan to help mitigate that. I might have missed it, but on the new retail version of the Gear VR, is there any fan integrator or any improvements to the cooling mechanisms?
I actually honestly don't know. I assume it's very similar to what we have for the S6. I don't know all the details for that, and I'm not even sure that that's all like completely finalized as it is right now. So it'll be hard for me to speculate on that. Anyone else? All right, thank you very much. Thank you for coming out today.